I'll scroll up also. So for the second part, you use this to find the potential and the spring constant. You want to find the spring constant, so just use this now. Here to here, okay. See, the total displacement of the block will be d plus that compression. So 1.9 plus 0.1 or 2 meters. Okay. So work done by friction will be minus mu mg s, because as the block is moving, again friction is acting opposite to the direction of displacement. So work done by friction should be equal to change in kinetic energy plus the change in potential energy of the spring. So let's say this is the state A of the system, this is the state B of the system. So apply this theorem now from A to B. Okay, so your work done by friction will become this much, where S is 2 meters now, because you're taking the full displacement from the starting point till the block comes to rest momentarily, because the spring is having maximum compression. Okay, people, anybody got the answer for this second part? Now you understood what's happening here, no? This block, which was of mass 2 kg, you know, this had started with the initial speed of 4 meters per second, and the coefficient of friction for us was 0.2, you know, and it went all the way up to here, where it compressed the spring through a distance of x naught. No? So the total displacement for the block, as you can see, I've written over here, is this. It is d plus x maximum, so it's 2 meters. So from A to B, the work done by friction will become minus mu mg s. So that will become minus of 0.2 into the weight of the block, which is 2 into 10, into the total displacement, which is 2 meters, which you are seeing here. It's 2 meters. And we're substituting this value 2 meters. So this should be equal to the change in kinetic energy plus the change in potential energy. So change in kinetic energy अभी कितना होगा? Final speed 0 है. So final kinetic energy 0 है. Initial speed कितना है? Minus half mv naught square. So this term will become minus of 1 by 2 into 2 into 4 square. 16 joule was the initial kinetic energy plus change in potential energy of the spring. So यहाँ पे spring का x कितना है? 0 है. It's at natural length. और यहाँ पे x's value is 0.1 meters or 10 centimeters. So this is plus half kx maximum square. So this will become plus half into that unknown value k into 0.1 square in SI units. So in this equation now you can see there's only one unknown. K is the unknown quantity which we'll find. Okay. So this side of the equation is becoming 8. Okay. So sorry, minus 8, and this is minus 16 is equal plus 0.01 by 2. So that is 0.005 K. Okay. So K, as you can see, is becoming 16 minus 8 upon 0.005. So K is equal to 8 upon 5 into 10 raised power 3 in newtons per meter, or we can say it is 80 by 3 Newton per centimeter. So this is the second part. We have to find the value of K. So this is how we have found out the value of K. Okay, so main thing you have to follow here is this equation, how we have supplied the values in this. The work done by friction is this term. The change in kinetic energy is this term. And the change in elastic potential energy is this term. And we substituted the values. Yeah, see, Ayush, how we are doing the last 4 steps now. See, for the block plus spring as a system, the work done by friction is change in kinetic energy plus change in potential energy from A to B. ठीक है? So A to B, पहली बात, my displacement is how much? It is the distance d plus the extension of this, sorry, the compression of the spring. So that is becoming 1.9 plus 0.1, so 2 meters. That is the displacement. So work done by friction is minus mu mg into this displacement. So that is how I've got the left hand side. Okay. Then on the right hand side, A to B, you can see that at A, what is the kinetic energy? The initial kinetic energy is half mv naught square. And what is the initial potential energy of the spring? Is 0 because x is equal to 0. Understood now? This is the initial state. In the first diagram, you can see the speed of the block is v naught, which is 4 meters per second, and the extension of the spring at that time is 0. Whereas at the point B, which is the lower diagram, when you're reaching the final state, what is the final kinetic energy? 0, because the speed of the block has become 0 at maximum compression point. Whereas what is the potential energy of the spring? It is half kx maximum square, because it has reached the value of x maximum, which is in fact 0.1 meters. Okay. So now your delta K is the difference of these two. Na? So change in kinetic energy is final minus initial. So that is why it's a negative quantity. Whereas the change in potential energy is going to be a positive quantity because the final potential energy is positive. So it's minus half mv naught square. The kinetic energy is reducing from this to 0, whereas the potential energy is increasing from 0 to half kx square. So that's why it's plus half kx maximum square. So that's what we have substituted on the right hand side. Is it clear now, Ayush? Okay, and final thing now, you have to substitute all the values in proper SI units. So make sure that you convert the 10 centimeters to meters and everything like that. Yeah, you have to be careful about that. Okay, so hope the values are clear in this question for all of you. Let's move on to another example next. Now in this example, we will take a vertical spring mass system. So we have suspended a spring vertically like this and suspended a block to the bottom of the spring. So the spring constant is, let us say, 50 newtons per centimeter, and the block's mass is 10 kilograms. Now, initially, the block is being held at rest. Such that the spring is in a relaxed state. Okay. And is now released So the block is released from this state. It's released at an initial speed of 0. Okay. We'll take the value of g as 10 meters per second square. So first of all, find the acceleration of the block just after it is released. Second, find its speed v and acceleration a as functions of x, where x is the downward displacement of the block. Okay. And once we found this, we'll find the particular values of v and v and a at x equal to 1 centimeter and x equal to 3 centimeters. And finally, we'll find the maximum speed the block will have, and eventually we'll find the maximum extension of the spring. These two things we'll find out. Okay. So don't worry about the last couple of parts. We will come to that. Let's start by understanding how to solve the first two parts of the question. Okay. It's an ideal spring, so it's a massless type of spring which has spring constant of 50 newtons per centimeter, and you're attaching this block of 10 kgs to it. Now, initially you're holding the block as an external agent. You're holding the block with some external force such that the block is at rest, but the spring is relaxed. It's at natural length. And you release it from this position. So the block starts falling. And as it falls, the spring gets more and more extended. So eventually it will hold back the block. Okay. So that's what you have to find, that as it falls through a distance x, what will be the speed v as a function of x and the acceleration a as a function of x. And from that we have to find the particular values of v in meters per second and the value of acceleration in meters per second square at the particular values of x of 1 centimeter and 3 centimeters respectively. So just try this out, people. So again, you can look at applying work energy theorem to find the speed, whereas to find the acceleration, you can use the free body diagram. So you can use a combination of methods, free body diagram and Newton's second law to find acceleration, whereas work energy theorem to find the speed. Okay, people, let's work out. So the first part is actually very easy. When you just release the block, at that point of time, the spring is at natural length. So the tension in the spring is how much? It's 0. So when you just release the block at t equal to 0, let's say, initial speed of the block is 0 and the spring is at natural length position. So the tension in the spring is 0. So there's only one force acting on the block, which is the weight, and that is giving it a downward acceleration. So A is equal to mg by m, or g downwards, just after you release it. But then after some time, when this block has made a downward displacement of x in comparison to this state, now it has made a downward displacement of x. So the spring has now got stretched by x. So the tension in the spring is becoming kx. So at that point of time, the acceleration and speed of the block will be such that mg minus kx is equal to ma. So the acceleration as a function of x will become like this. So acceleration will be 10 minus 50 by 10 into x, or 10 minus 5x. Where x is in centimeters, so acceleration is in meters per second square, because this was 50 Newton per centimeter divided by 10 kg into x in centimeters. So the unit of this thing will become meters per second square. So this is the acceleration as a function of x, where x is in centimeters and acceleration is in meters per second square. So that's one thing. But we also want to find the speed as a function of x. So let's look at that next. So to find speed as a function of x, use work energy theorem. So if you take the block plus the spring plus the earth as your system, then you can see that the change in kinetic energy plus change in gravitational potential energy plus change in spring's potential energy is 0, because there is no external force doing work and there is no non-conservative force doing work. Mg and spring force, they are both internal conservative forces for this system. Okay, so you can use this to find V as a function of x. So try this out now. This will give you the answer for the second part. Okay, so hope you've used the equations to write down the values. So you can see going from this state in diagram 1 to this state in diagram 2, you can calculate the change in potential energy for the spring, the change in gravitational potential energy and the change in kinetic energy. See, here it started from rest and here it has a speed v by the time it reaches here. So the change in kinetic energy will be plus half mv square. It's going from 0 to v. Then it's coming down through a distance x. So the change in gravitational potential energy is minus mgx. And the spring is again going from a state of x equal to 0 because it's at natural length to a state of extension of x. So the spring's potential energy is increasing by half kx square. So this is your work energy theorem. So from this you can see that your kinetic energy is this type of an equation. Okay. So your kinetic energy you can write as the mass of the block was 10 kg. So 100x minus half k. Now in this we'll write k in the SI unit. So 50 into 10 raised power 2 newtons per meter multiplied by x square. So this is your kinetic energy as a function of x. So from this you can also see that your speed as a function of x will be square root of 2gx minus k by m x square. That is square root of 20x minus k by m will become 50 into 10 raised power 2 newtons per meter divided by m was 10 kg. So that's 500 x square. So this is your v as a function of x. Whereas this was your acceleration as a function of x. So these are the two parts which are giving you the answer for this thing. No, that's not true. X is in centimeters, no, beta. So for example, substitute x equal to 1 centimeter, you will see you will get a positive value. Here, this is in SI units, no? So you have to substitute x in meters. So remember in this equation, x is in meters and v is in meters per second because I've substituted everything in SI unit. So that's what we'll look at next, the third part. So we want to find out v and a at x equal to 1 centimeters. Okay. So we just saw that v is given by this relation, square root of 20x minus 500x square. But this is in SI units. Okay, so we will substitute in this x equal to 1 centimeters or 10 raised power minus 2 meters. So we will get v okay, minus 500 into 10 raised power minus 2 squared. So this is becoming 0.2 minus 5 into 10 raised power minus 2. Okay. So that is be very nearly 0.4. meters per second. Something slightly less than 0.4, something like 0.398 or something. Sorry, 0.38. Actually 0.39. So this will be the speed is approximately 39 meters per second, sorry, centimeters per second at a displacement of x equal to 1 centimeters. And acceleration was g minus k by mx. So 10 minus 50 Newton per centimeter divided by mass in kg into 1 centimeter. So here I can substitute in centimeters because I've taken this in centimeters per second. So acceleration will become 5 meters per second square downwards at x equal to 1 centimeters. So kinetic energy will only take positive values. So x will not have a range where kinetic energy becomes negative. Okay. So this relation, this had come from the fact that half mv square was mgx minus half kx square. No? So the kinetic energy, when we substituted all this, so this was like this one. So note here that the kinetic energy is only greater than equal to 0. So when we look at the graph now, kinetic energy versus x, on its own, it's a parabolic graph like this. But we won't take the part where kinetic energy is negative. We'll only take the part where kinetic energy is non-negative. It is either 0 or positive. Only these values will be taken. 0 to some maximum displacement, where the kinetic energy is becoming 0. So we'll discuss more about this graph and this range of motion also in the next part. But first we also have to calculate the B part of this. We have to find V and A at x equal to 3 centimeters. So just do a repetition of this calculation, but for x equal to 3 centimeters. See, you will get an interesting result, okay, which is why I've asked you to do both these parts, 1 centimeter and 3 centimeters. So just use the same method here to find out from the work energy relation, we had got V as a function of x, okay, and from the free body diagram, we had got acceleration as a function of x, which was like this. So just work this out, people, for 3 centimeters. Everybody got the answer for V and E at, yeah, what is the value? No, V will be in same direction. Actually, V, I'll show you, keeps alternating direction actually. Because what happens now, the block will keep oscillating actually. When we discuss about the maximum displacement and maximum speed, now we'll discuss. The block never really comes to rest forever. Once you release it from this position, it keeps oscillating vertically. So it keeps going up, down, up, down. So every time it's going down through 1 centimeter, its speed will be that much, 0.39 meters per second. Then on its way up again, it will be upwards, but 0.39 centimeters per second, like that. But the acceleration has fixed value in both magnitude and direction. So at 1 centimeters, it is 5 meters per second square downwards. And later, when it is at 3 centimeter displacement, it's going to have the same value, 5 meters per second square, same magnitude, but direction opposite. Okay, so same speed, but opposite acceleration of 5 meters per second square. Yeah, it's continuing to go down, and then eventually it will come up, but it will go down with deceleration. Okay, whereas at 1 centimeters, it's going down with acceleration. I'll explain in a moment, it will become clear. So see, the formula for speed is square root of this thing, no? 20x minus whatever. What was it? 100x square? Sorry, 500x square. So actually, this is a plus minus quantity, but we are calculating speed. No? So speed is magnitude of velocity. So we don't take the negative root. Speed we just take as a mod. Okay. So here you substitute x as 3 into 10 raised power minus 2 meters. So you get this as 20 into 3 into 10 raised power minus 2 minus 5 into 10 raised power 2 into 9 into 10 raised power minus 4. Okay, so this is becoming 6 into 10 raised power minus 1 minus 4.5 into 10 raised power minus 1. Okay. That is again square root of 0.15. Okay. So this is speed. So we don't write it as plus minus. It's just the magnitude of velocity. So it's not a plus minus quantity. Whereas the acceleration, that has a specific direction. Okay. So for the acceleration, what is happening? The spring force at this point of time is becoming 50 Newton per centimeter into 3 centimeters. So it's becoming 150 newtons. Okay. Which you can see is exceeding the weight. The weight is only 100 newtons. So the acceleration is opposite in direction now. The acceleration is upwards. So E is equal to kx minus mg by m, upwards. So the acceleration is 5 meters per second square upwards at x equal to 3 centimeters. Okay. Now in a moment we'll understand why this is happening. Okay. Okay, so now before we proceed to the next partner, the maximum extension and maximum speed, let's understand something over here. That if we compare the motion of the block at various stages, okay, so we saw initially the speed was 0, x was 0, and it had a maximum downward acceleration of g, okay, which was 10 meters per second square. Now, just now we saw that by the time it comes to a position where x has become 1 centimeter, its downward acceleration has reduced to 5 meters per second square because there is spring force kx acting on it, okay, and it's also got a downward speed of nearly zero point 0.4 meters per second, close to that, okay. So here what is happening at this stage, if you see, mg is greater than kx, so it is accelerating downwards, okay. But by the time we reach a displacement of 3 centimeters, so the extension of the spring is becoming 3 centimeters. Now at this stage we are seeing that kx is dominating, so it's having an upward acceleration of 5 meters per second square. So it's having an upward acceleration means that at this stage what is happening, kx is dominating over mg, so its acceleration is upwards, and again its speed has become nearly 0.4, but it is decelerating because it's going down but with an upward acceleration, whereas at this stage is going down with a downward acceleration, so it is accelerating. So weight is dominating, so it's accelerating, but then it crosses that and now kx dominates over weight, so it's decelerating. So that means it will reach some position here which I have not yet calculated, but at some position what will happen, that the block will come to rest, its v will become 0, and at that point of time the extension will become maximum, and this is what I want to calculate. Whereas in between these two there would have been some position where the speed would have become 0 because इसके पहले वो accelerate कर रहा था और उसके बाद में वो decelerate कर रहा है, so it would have reached some position where the speed would have become maximum, which we'll calculate. So we'll also understand that v will be the maximum when acceleration is 0, because before that speed is increasing, okay, then it reaches the maximum value, and then after that the speed is decreasing till it comes to rest, okay. And it has started from rest like this, okay. So that is why we are getting, okay, and then to after that also the motion will again continue after this. So what will happen after this stage is, from here it will have a very strong acceleration upwards. In fact, we'll see that when it reaches this position the acceleration will again become 10. I'll show you that how this is happening, okay. So it will again go up, so this time it will again come to this position where x is equal to 3 centimeters. Now this time it will have an upward velocity of 0.4 meters per second and an upward acceleration of 5 meters per second square. Okay. Then it will continue up. Okay. So it's a full oscillation cycle. It will reach some position here where I want to calculate x, but speed will be maximum. So at this stage its acceleration will be 0. Then from there it will continue further up, where now its acceleration will be downwards, but speed will continue to be upwards till it comes back to where it had started from, where x is 0, v is 0, and it has a downward acceleration of 10. So this has completed a full cycle of oscillation. Now this whole thing starts again. So it keeps going up and down like this, from here to here, then back like this. So this series of motion keeps occurring because there's no loss in energy, no loss in mechanical energy for the system. So it perpetually oscillates. In real life, such a perpetual oscillation will not happen because there is air resistance. The spring will not be ideal. But if we do such an experiment inside a vacuumized chamber where there's no air resistance and we have a nearly ideal spring, then at least it will happen for a very, very long time. It's possible to demonstrate that, experiments where the motion is almost perpetual. It can last for like months and months and months and even more. Okay. So now the next thing we need to do here is we need to find out the maximum extension of the spring and the maximum speed of the block. So we're coming to that next, but first understand this series. Okay. So again here kx is dominating over mg. It has an acceleration upwards, but this time it has a speed also upwards. So it's accelerating upwards. Okay. Then at this point where a is 0, v is maximum, but it's upwards. Then it reaches a position here where kx is less than mg. So it has an acceleration downwards. So it's on its way up, it's decelerating. And it comes to rest over here. Yes, what happened, Itanju? What is the question? Yeah, write down this whole series. I've already explained it twice. You can go through the video later. V and A are in opposite direction, na? So it's decelerating. You see the direction of the vectors, na? V is upwards and A is downwards, so it's decelerating. In each of the diagrams, I've shown you the direction of V and A. So wherever V and A are in same direction, the body's speed is increasing, so it's accelerating. And wherever V and A are in opposite direction, its speed is decreasing, so it's decelerating. Okay, Kunj, let me verify your answers. Yes. So now that you've understood this whole pattern, so you'll understand where it is reaching maximum speed. It's reaching maximum speed here. This is where speed is maximum when acceleration is 0. This is on the way down, and then again on the way up, it's reaching maximum speed again at the same position where acceleration becomes 0. So you'll understand that V is equal to V max when the instantaneous acceleration is 0. So that means Kx is equal to mg, or x is equal to mg by k, which is going to be 100 newtons divided by 50. So that 2 centimeter position is the mean position. So x equal to 2 centimeters, we'll call this the mean position, because this is the position at which acceleration is 0 and speed is maximum. In any oscillation, that is called the mean position. So this is the mean position of the vertical acceleration, sorry, the vertical oscillation. Okay. You can see this block is undergoing a vertical oscillation. So now in the work energy relation, we have to just use this. So half m V max square is going to be equal to mg into 2 centimeters minus half k into 2 centimeters square. So substitute the values. So half into 10 kg into this maximum speed square is equal to 100 into 2 into 10 raised power minus 2 minus half into k, which is 50 into 10 raised power 2 into 2 into 10 raised power minus 2 square. So 5 V max square will become 2 minus, now this we'll have to calculate. Okay, so this is half into 25, okay, into 4 into 10 raised power 3 minus 4, so that's minus 1. Oh, sorry, this is 5, not 25. That's right. So this will be 1. So V max will become 1 by root 5 meters per second. Okay, so that is root 5 by 5, or approximately the maximum speed is nearly 45 centimeters per second. This is the value you got, Kunj. You got it as 60 centimeters per second. Okay, just check my calculation also once. I think it's all right. Yeah. Yeah, this is correct. Whereas what about the maximum extension now? How we'll calculate the maximum extension? So you'll understand the maximum extension is happening at the position where V is 0. That is at the bottommost point or the lower extreme of the oscillation. So coming back to this oscillation, you can see that this position is an extreme position of the oscillation. This is the top extreme, and this position is the other extreme position, which is the lowest position. And this is again the extreme position at the top. Whereas these positions here in between are the mean positions. So at the mean position, the speed is maximum, the acceleration is zero. Whereas at the extreme positions, the speed is zero and the acceleration is maximum. So for the next part, x maximum, we have to calculate x at the lowest point, that is the bottom extreme, where the speed is again zero. Okay, Kunj. And the maximum extension you are getting how much? 4 centimeters. That's correct. Okay. So I mean parametrically it will come out to be twice of mg by k. So that will come out to be 4 centimeters here. Okay, so as I said, to calculate the maximum extension of the spring, the last part of the question, we have to just use this concept that at the lowest point, what is happening? The speed is becoming zero. So we had the relation that the kinetic energy half mv square was equal to mgx minus half kx square, which was 100x minus 5000 by 2 x square like this. So in this, when we put v equal to 0, the corresponding value of x will be x maximum, which we can find out. Okay, so this will give us two roots, x equal to 0, which is the starting point, and x equal to, this will come out to be 4 by 100 meters, or that is 4 centimeters. This is the lowest point. So the maximum extension of the spring will be 4 centimeters. So this again brings us to the graph of this relation also. If you look at this relation's graph, the kinetic energy, take x common, is like this. It is x into 100 minus this, or you can even write that as this is your kinetic energy as a function of x. But remember, kinetic energy can never become negative. So we have to take only that part where it is positive or non-negative. So your graph of kinetic energy versus x will be this sort of a graph, where this is your maximum of 4 centimeters. This is where your kinetic energy is maximum. It's a parabolic graph, so it's the vertex is the midpoint of the roots. So this is the mean position, whereas this is the extreme position. So the block continuously oscillates between 0 and 4 centimeters. And right in between the two is the 2 centimeter position, where the block is at the mean position. So every time it is at the 2 centimeter position, it's having maximum kinetic energy or maximum speed. Okay, so hope the analysis of this question is fully clear now. You can see that. Okay, so now we are coming to the last couple of things about work by energy. So we'll understand the definition of power today. So power is the rate of work done with respect to time. Okay. So the power, or we can say the instantaneous power, say P, developed by a force F, is the rate of work done by that force with respect to time. Now we know that work done by the force in general is integration of F dot ds. So in differential time dt, the small work done is this. So we can substitute this here and we can say that the instantaneous power is F dot ds by dt. And we know that ds by dt becomes the instantaneous velocity. So by that definition, we can also reduce power to the dot product of force with the velocity at the point at which the force is acting. So while the definition of power is rate of work done with respect to time, but formula wise it also works out like this, that power, which is the rate of work done with respect to time, is equal to F dot B. This is the instantaneous power delivered by a force F, where V is the instantaneous velocity of the point of application of the force. Where you know that basically F dot V is the scalar product, FV cos theta. So the force is acting at a point like this, while the point's velocity is like this. The angle between them is this. Yeah, next couple of lectures we'll be discussing H.C. Verma questions and also from the module. Okay, now the unit of power is watts. 1 watt is equal to 1 joule per second. There is also a unit of power, a non-standard unit, which is from the old British system, which is still used in automobile engineering, and that is the horsepower, or sometimes also called BHP, British horsepower. Where one British horsepower is nearly 746 watts. Okay, but this is not really used for our purpose in mechanics much. This is the unit that we use. This is just out of your general knowledge. You might have heard it in automobile industry. In automobile engineering, this term is used. British horsepower or horsepower. Because it is not followed by any of the standards. It's not a standard system. It's not part of a standard system of units. SI unit is standard international unit. It's not part of that standard set of units, so it's a non-standard unit. It's just a matter of convention that that unit is not used in the standard system. No, you don't need to learn the convention. That's why I tossed it out. You don't need to learn it. It's just that for your general knowledge, you would have heard this term in many places. So if you know what it means, so it means this. Okay. So for example, we have a situation like this, let's say, that a block is placed on a rough surface. So this surface has a coefficient of friction equal to 0.2. The mass of the block is 5 kg. Okay. And it's at rest at T equal to 0. Now we start pulling the block with an external force like this, which is of magnitude 25 newtons, acting at an angle of 37 degrees. Okay. So from T equal to 0 onwards, okay, a constant force F starts acting on the block. So we have to find the instantaneous power delivered by the force F and friction at the instant 2 seconds. At the moment 2 seconds, what is the instantaneous power delivered by each of these two forces? So what we'll have to do here is a little bit complicated. You will have to first find the acceleration of the block. Okay. And from that you can find out that at T equal to 2 seconds, what is the velocity of the block? And once you found the velocity, you can find the power delivered by F as F dot P. You can find the power delivered by friction as friction's dot product with velocity. So this is what we have to do in the question. So just try this out, people. This is the standard type of question for the concept of power. Take G as 10. Take acceleration due to gravity G as 10 meters per second square. I'll be done in 2 minutes. Okay, people, let's find out the values here. So first thing, as I said, you have to find out the acceleration. So for that, you need to resolve the forces. So F cos theta here will become 20 newtons. F sine theta, when you resolve, will become 15 newtons. So the normal reaction will be equal to the weight minus, so the weight is 50. So 50 minus 15, it will be 35 newtons of normal reaction, because mg is 50 newtons. And that means that the kinetic friction acting, which will be mu n, will become 0.2 into 35. Okay, so that is 7 newtons. So the kinetic friction of 7 newtons will be acting. So that will tell us that the acceleration of the body will be F cos theta minus kinetic friction divided by mass. So that is 20 minus 7 divided by 5. So that is 13 by 5. Okay, or 2.6 meters per second square. This will be the acceleration. So at t equal to 2 seconds, the velocity of the block will become et. So v will become 5.2 meters per second. So now once I know the value of v, its magnitude is 5.2 meters per second, I can see that my external force F is having a magnitude of 25 newtons and acting at an angle of 37 degrees, whereas my kinetic friction is acting in this direction opposite to the velocity, and its magnitude is 7 newtons. So the power developed by each of them, the power developed by F will be F dot V. So that is 25 into 5.2 into cos 37. So that will become 104 watts. So it's a positive of 104 watts. Whereas the power delivered by friction, when you do this dot product, you will see it will become minus of the frictional force, because the angle is 180 into the velocity. So this will become a negative power. So like work done, power can also be negative. So this will be the power delivered by the frictional force. This is the power delivered by the external force F. So this is the answer to this question. Okay. So we are now done with the concept set of this chapter, work, power and energy. So next couple of lectures we will spend on discussing the questions and doubts and things. So please try to complete the maximum part of HC Verma for the next lecture, and also start working on the module questions, so that subsequently next week we can discuss the module exercises also. So that's it for today, people. Wish you all the best.